Next slide. So this is the BAM. This is how the internal structure looks like. I have not seen it yet. It's on the way coming. So I know Dan and Allison will come in here to answer some questions, those that I may not be able to answer. Next slide. So it's all still about the BAM. So BAM, it uses the 14 carbon beta ray source that emits a constant supply of beta rays. So we have the detector that detects the attenuation of beta rays by particles, just like the frequency, that is oscillation thing. So the detector detects, so the amount of attenuation is a function of the mass of the absorbing material. So how much oscillation determines the mass of the particulate. Next slide. So low-cost sensors, low-cost air quality sensors for gas. The gas sensors, they're generally electrochemical or metal oxide sensors. So in this case, the gas molecule diffuse through a selective barrier and go through reduction oxidation reaction on an electrode to create a current. So the current is proportional to reaction rate, which can then be used to calculate the species of the concentrations. So for the metal oxide, the gas molecules absorb onto a selective porous layer and change the electrical resistance of the layer. So that change in the electrical resistance is also measured. It corresponds also to how much of the gas. Next one. So the gas enters the sensor by diffusion, and then gas permeable membranes using this thin film. So it enters by diffusion. Then we have the working electrode, the counter electrode, and the reference electrode. Three of them play their different roles. So at the working electrode, we have the oxidation or reduction reaction happening. Taking example of the carbon monoxide sensor with aqueous electrolyte, that reaction there shows what happens. And then for the counter electrode, this completes the circuit between the working electrode, then balancing the redox reaction, and then we have what we have there. And then the reference electrode is kept at a constant potential. So this helps the accuracy and stability and linearity of the sensor response to current. Next one. Just an example of a metal oxide sensor. Just showing the electrical resistance, measurement of the change in electrical resistance. So this is for oxygen containing compounds. So oxygen absorbs the metal oxide here. So the negative charge from the oxygen atom are trapped near the surface. The first one we looked at was carbon monoxide. So now, here, carbon monoxide are oxidized by the negative ion, resulting in a release of electrons to the bulk material. This release of electrons increases the conductivity. So change in resistance is also measured here. Next slide. So there are some issues with gas sensors. You can see most of the low-cost sensors we have, most of them are particulate sensors. So there are some issues that sensor response sensitive to environmental conditions, very sensitive. So what you record might not be the actual thing because of the sensitivity to the environment. It's like temperature and so on. So it could alter the result, and you have a lot of interferences, that of response time, the drift over time, limited lifetime also. For gaseous sensors, you will have to change and change. Like, for instance, an experience I had with air quality egg, the PM sensors still working, but the gaseous started showing very funny results. And we found out that we needed to replace it, and had to replace before it started working well. So it has a short life span. Next one. The sensitivity, what we just talked of. I think I will leave this one. Next slide. Reference gas monitor. I'll also leave it. It's part of what is here. I've already talked of it. How it's, can you move to the next one? The gas analyzer still move. Okay, we can leave it. So in this case, for ozone, the UV radiation that is absorbed by ozone is proportional to the ozone concentration. So it will be easy to measure. So a beam of UV radiation generated from a mercury lamp is absorbed by ozone. So the amount that is not absorbed is detected by the photodiode, and that is used to calculate the ozone concentration. So you know the amount that is put in there, and you know what is absorbed, what is not absorbed. Then you'll be able to, from that, subtract from what you had, what has gone out, then the other one is absorbed, and then you know that that's the quantity, or the concentration of the ozone. And it follows the Beer-Lambert's law, which concentration is directly proportional to the absorbance, to the absorbance. So the more you see the absorbance, the more you know the concentration. So directly proportional. So you can use Beer-Lambert's law and you get the result properly. Next one. So this is also showing those different pollutants at what wavelength they absorb. Like I just talked about the ozone absorbing the light, the different pollutants they absorb at different wavelengths. So with that, you'll be able to know that be able to differentiate from what, differentiate and know the particular pollutant you have seen because of the different wavelengths that they absorb. Can you move it? So I'll still leave this one. So it's just the same thing, absorbing of UV light. Next slide. So calibrating and correcting low-cost sensors. Calibrating and correcting low-cost sensors. I think most of us, we know Mike, and this is part of his work. So let's see in the next slide what to do. So traditionally, what is done is placing the sensors side by side with the reference monitor. That is what is called co-location. And then you obtain the data at certain times, the two data from the local sensor and data from the reference monitor, and carry out a regression, either multilinear regression or machine learning. Somehow you use that to calibrate and validate the data that you obtain from your low-cost sensor, calibrating it with what you have from your reference monitor, used either multilinear regression or machine learning or probabilistic method, and carry out that validation. So, and what are the data that what are the parameters that you put in that is normally useful for this validation? You will use temperature, you use the PM output, you can use relative humidity. So these are the parameters that you can use to compare between the reference monitor and the low-cost sensor. And from there, you can get some correction factors and then correct it. And then you can take your low-cost sensor to wherever you want to monitor and know that it's going to give a good result, taking care of, since the correction factor is also taken care of. Next slide. So we have these questions that we need to answer here. What kind of sensor or reference monitor should I use? What conditions should the co-location occur under? How long should I co-locate for? How long does the correction remain valid? What kind of statistical method or model do I want? What input variables do I want in the model? Next slide. So to answer those questions, what you do, you co-locate as many sensors as you want, you co-locate them with the reference monitor. So you locate in a similar microenvironmental condition. Some time ago, we had a particular low-cost sensor, but we did not have any reference monitoring station in Nigeria. So our partners had to co-locate with reference monitor in UK and then brought it here. So we just managed that, but it is advisable that you co-locate under that same micro environment, under the same condition. So like what we have now in Nigeria, so whatever you co-locate there is valid. So, and co-locate for a long enough period to span a range of environmental conditions. Like you have the rainy seasons in Nigeria, you have the dry seasons, you have the harmattan and so on. So you can, it's advisable to co-locate for as long as so that it will cover those. If possible, leave a sensor until permanently, or leave a unit permanently at the co-location site. You can use the other sensors where you want to, and then you can leave one permanently there to be able to monitor and do the corrections based on the seasonal changes. So for correction, pick an open source reproducible statistical model over something that is proprietary. So you can see online, look for an open source statistical model. It's advisable to use that. Check for linearity if using linear regression. That is what you will check for and do some corrections. As reported, PM data, relative humidity, possibly temperature, like I've mentioned before, those are the input variables that you should use when you're calibrating your local sensor with a reference monitor. Include robust model validation. Example is the k-fold cross validation, which I will mention in the next slide. So